Automotive Central. The show with the biggest, baddest, heaviest, tallest, longest, loudest, meanest machines on the planet.
They are enormous. You can fit a house in them.
Machines designed to do man's dirty work, so to speak.
We can go from ground level to some 50 feet in the air in less than 16 seconds with 80 tons of dirt.
Machines with muscle.
This engine's got 16 cylinders. It produces about 2,300 horsepower.
Beasts with big appetites.
This is our fuel tank, 1,580 gallons.
And stadium-sized devices designed to unlock the secrets of the universe.
Over 7,000 pieces of glass that weigh approximately 150 tons. There's nothing like this anywhere on Earth.
Machines that are all about size.
They're just fantastically enormous. I don't know which other way to say it.
These are the machines bold enough to call themselves the world's biggest. Some of the biggest mobile machines on the planet are walking draglines. Excavators used in surface mining to wrest coal and other minerals from the earth. Here at the Black Thunder Mine in Wyoming, a 2570 WS dragline built by Bucyrus International of South Milwaukee, Wisconsin, uses a bucket big enough to park 6 cars inside. The bucket is suspended by cables from a massive 360-foot long boom. When digging, the operator lowers the bucket into the pit. In the machinery house, which is the size of a small warehouse, electric motors drive giant drums, which spool 5-inch steel cables like the reel in a fishing pole. This drags and lifts the bucket, filling it with overburden, the material covering the coal seam.
He's probably moving 300,000 pounds or 400,000 pounds of dirt each time. It takes a lot of power, 25 to 30,000 horsepower to hoist that load, heavy load, and hoist it within a matter of seconds.
Everything on board is driven by electric motors, and a giant extension cord supplies enough electricity to power a small city. Bucyrus builds the biggest draglines in the world. Here in the Bucyrus shop, machinists turn out parts for a behemoth that is so large, it can't be assembled until the components reach the mine. Putting it together can take more than a year.
The total dragline weighs like 16 million pounds. It takes over 2 years to manufacture. It takes 128 shipments to ship a dragline.
How do they make a giant machine? With giant machines, like this MOG gear cutting machine.
This particular gear that we have on this MOG, which is one of the largest MOGs that we have in our facility, actually cuts this gear by rotating in a circle and having cutters that actually cut the profile of the teeth. This particular gear takes over 100 hours to manufacture just to cut the teeth in it.
These massive parts will eventually merge into a machine that dwarfs everything around it. It may be the industry's cutting edge, but even this dragline can trace its roots back to a much smaller machine and an American inventor who believed he could ease the growing pains of a burgeoning country.
A man called William Otis invented the first steam shovel. This was back in 1835, and his machine was quite a revolution because prior to that, all the excavation work that was done on railroad construction and everything else was done by hand.
Although a big improvement, cheap labor and Otis's untimely death prevented the steam shovel from scooping up a big share of the excavation business. By the late 1800s, contractors finally realized manpower just wasn't as efficient. Not mechanizing was becoming a pain in the neck, and the back, and the shoulders. Rushing to massage the industry, two historic equipment manufacturers were born in the 1880s. The Marion Steam Shovel Company and the Bucyrus Company began building shovels, igniting a legendary rivalry that would use the most massive engineering projects of the 20th century as a stage.
Throughout the entire histories of these companies, they developed a very intense rivalry. One of the first was in the construction of the Panama Canal. Both companies sold large numbers of steam shovels for this massive project. In the end, Bucyrus sold more. Bucyrus sold 77 shovels. Marion sold 24 shovels.
There was always fierce competition between the crews operating these machines. The performance of the best shovels were reported daily and weekly in the Panama Canal Record, and those were broadcast throughout the world. I mean, people were behind this effort. They wanted to know what was going on.
During construction of the canal, 1904 to 1914, Bucyrus and Marion machines moved 260 million yards of earth and rock, enough to fill 83 football stadiums. The heated rivalry continued through the 1920s. Both companies designed bigger and better machines. One improvement gave excavators freedom to roam: the crawler track.
The first steam shovels were built on railroad tracks. The crawler track appeared first on crawler tractors in the early 1900s, and then it was applied to shovels and draglines. So a shovel mounted on crawler tracks could exert a low ground pressure and not sink in out of sight, like a wheel machine might do.
More mobility equaled more productivity. Bucyrus and Marion fought to capture the lion's share of the excavator business. The shovel and dragline business boomed during the next several decades. Excavators helped build roads, tunnels, and dams. Draglines and shovels unearthed coal, gold, copper, and other minerals. By the 1950s, deeper surface mines demanded bigger and bigger machines. Ever larger excavators tore into the earth. In the 1960s, the long-simmering Bucyrus-Marion rivalry would culminate in a race to build the biggest machine on the planet. Next, the Battle of the Behemoths. The battle for biggest glowed red-hot in the 1960s. Fueled by America's growing use of coal, excavators supersized. The Marion and Bucyrus companies built the biggest behemoths, locked in a rivalry more than 70 years old.
Bucyrus would build the biggest dragline or the biggest shovel. And the next day, the other company would build the biggest one.
In the early 60s, the rivalry between companies moved from being a race to build the next big excavator to another kind of race.
To achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
In the mid-60s, NASA engineers worked to perfect the Saturn V rocket, a 363-foot tall machine which weighed 8 million pounds. But before the U.S. could get a man to the moon, they had to first get a rocket to the launch pad. The rocket would be housed in the Vehicle Assembly Building, or VAB, 3.5 miles from the closest launch pad. NASA considered several methods for moving it, including a rail line, a canal and barge, and a crawler transporter. NASA wanted to go with the crawler system. The question was, could it be built? NASA turned to the only companies who could do the job.
NASA commissioned Bucyrus to design a transporter, and Bucyrus produced all of the drawings for a transporter. And at the end of that effort, NASA, being a government agency, put the construction of the transporter out on bids. Marion had a lower bid and got the order.
Marion won this round and started manufacturing 2 identical crawler transporters. In 1965, assembly began at Kennedy Space Center. Road testing soon followed. Each transporter was 131 feet long and 114 feet wide, having roughly the surface area of a baseball diamond. It rode on 8 giant crawler tracks, 10 feet high and 41 feet long. Each track had 57 shoes, weighing 2,000 pounds apiece. In June 1967, the transporter first rumbled into service, carrying on its back a Saturn V rocket for the unmanned Apollo 4 flight. In the next 10 years, the crawlers racked up more than 1,200 miles. After the Apollo program, the crawlers continued serving their country. After a few modifications, the same 2 crawlers shuttle the shuttle today.
We bring the crawler transporter over to the VAB. When we get the okay to enter, we drive in under the mobile launch platform. Once we're under there in alignment, then we lift the entire assembly up off its mounts, about 18 inches high. We're lifting 12 million pounds at this point.
The crawler, powered by 2 2,750 horsepower diesel engines, moves the shuttle to the pad at the blazing speed of just under 1 mile per hour.
The 2 crawler transporters are only 2 in the world. And without them, you don't have a space program.
In the mid-60s, even as Marion was busy building the NASA crawlers, it was also about to give birth to a monster the likes of which the world had never seen.
Each component was so huge that it had to be specially designed in the factory, and Marion in fact had to develop new machine tools. Huge gears, huge crawler track components, huge hydraulic cylinders. These were all of a size that had never been made before by anybody.
The Captain at 15,000 tons was the largest mobile land machine ever built. Completed in 1965, the Captain was a classic stripping shovel, but a really, really big one. Used to remove overburden that covers coal deposits, the Captain towered 21 stories and boasted a 215-foot boom. It moved around on 8 enormous crawler tracks, each 45 feet long and 16 feet high. With each bite, the Captain swallowed 180 cubic yards of material. The Captain was a mighty machine. But Bucyrus, not to be outdone, introduced a behemoth of its own. In 1969, Big Muskie shook to life. A dragline like no other, the largest single-bucket digging machine ever created. From tip to tip, the machine was longer than 1.5 football fields and stood 222 feet tall. Its bucket could hold 220 cubic yards of material. This monster didn't roll or crawl around the job site. It walked.
When draglines were developed in the early 1900s, they were mounted on rail tracks initially. They had problems sinking in the ground, so there was a new method was invented by Oscar Martinson in 1913, and he developed what is called a walking dragline.
With hydraulic shoes 131 feet long, Big Muskie stood up, scooted back, and sat down. The machine's enormity alone generated a lot of excitement.
This is a 220-yard bucket. 2 Greyhound buses could just barely park inside the bucket. So in the dedication ceremonies, I mean, they had tents set up. They had people from the surrounding area and from the mining company all invited to this dedication. And this was an event.
An event complete with marching band. But like the flesh and blood monsters that came before them, these dinosaurs were destined to become extinct. The industry simply didn't need anything larger, and environmentalists opposed them. These two machines would prove to be the largest ever built. In 1991, both machines stopped breathing. A fire broke out in the captain's engine compartment, gutting the machine. Repairs were too costly and it was scrapped in 1992. Big Muskie ground to a halt because of the Clean Air Act, which suffocated the demand for the high-sulfur coal it was unearthing. It fell to the salvage man's torch in 1999. For 120 years, the two companies were locked in a battle of the behemoths. But in 1997, Bucyrus purchased Marion, ending the rivalry.
Bucyrus bought out the Marion Power Shovel Company in recent years, and that was difficult at first for us to accept the enemy. However, we've gotten to know those people very good, and we're really one big family now, just trying to produce the best product.
The big machinery building business has dramatically changed since the late 1800s. So too has the American mining business itself. Before the 1960s, the surface coal mining industry earned itself a bad reputation for abandoning a site once the coal was depleted, without returning the land to its original condition, leaving it basically useless.
Today, and since the 1960s, that situation has totally changed. There are regulations in place. The companies have to do good reclamation. They salvage the surface soil in several layers, just how it was found, and put it back in the same sequence.
Although today's stricter reclamation laws mean these giant machines not only carve up the land, but in most cases must restore it once they're finished, some surface mining methods remain controversial. Next, a machine that throws around 65 tons, like a feather. The U.S. imports over $1 trillion of goods a year. 46% of that comes by way of behemoth container ships. Some ships can carry more than 5,000 boxes, stacked in and on the ship like building blocks. At the dock, they've got to be loaded and unloaded. That's the work of giant gantry cranes. A gantry is like a table supported by 4 legs.
What we have behind us are 6 post-Panamax gantry cranes. Post-Panamax gantry cranes, all that means is that they can handle ships that cannot travel through the Panama Canal. They are electric cranes. From the ground to the cab, they're about 120 feet. And then from the ground to the apex, about 175 feet.
These are 65-ton gantry cranes, meaning they can lift 65 tons of weight. The gantry legs run on tracks, allowing the crane to move parallel to the ship. When a ship comes into port, crane operators attack the cargo, unloading and loading simultaneously. From the control booth 120 feet up, the operator orchestrates a dance of sorts, throwing 50-ton containers around like toys.
A computer develops a loading plan for the particular ship. We try to keep the heavy cargo all below deck and the light cargo up on deck to keep the riding moments of the ship where they need to be.
In the equipment house at the rear of the machine, electric winches wind steel cables which do the lifting. These cranes are big, but not quite big enough.
The world's largest cranes are on their way. They're currently being built in Shanghai, China. We have 12 that are coming. Their capacity has increased from 65 tons to 100 tons. In our industry, they're the biggest gantry cranes in the world.
What is 2 stories tall, can lift the weight of 40 cars over its head, and weighs more than a 737? The Letourneau L2350, the largest front-end loader in the world. The Letourneau Company of Longview, Texas builds these giants to load coal, gold and copper ore, and other minerals into equally giant trucks.
Well, this is a 53 cubic yard rock bucket. Again, the machine has a total hoist capacity of 80 tons. To put this in perspective, the 53 cubic yard capacity is equivalent to about 5 normal dump trucks that you might see going up and down the road.
Wheel loaders are relatively young in the excavator family. In the 1920s, several implement manufacturers began building scoop attachments that fitted to the front of farm tractors. It wasn't until after World War II that manufacturers began making special-purpose loaders. Since then, they've grown up. The Letourneau Company has a long history building front-end loaders. But this is the very first L2350 to roll off the assembly line. Near the plant, there's a test site where the machine is put through its paces.
The need for the 2350 was born from the need to load bigger trucks. The dump trucks are getting bigger and bigger. If you can move more dirt with less people, that's the name of the game.
Engineers worked for 2 years to design the 2350. Their goal was to build a machine capable of lifting 50% more than its predecessor.
The dilemma that we faced were tires. There just was not a tire big enough. So we partnered with the engineers at Firestone to develop the world's largest tire. The tires are 13 feet tall, they're over 5 feet wide, and they're truly the biggest pieces of rubber that you'll see.
Letourneau builds many of the parts for the 2350 at their Longview plant. The company even operates a steel mill.
That's what we have here is an L2350 frame. Well, this is very early in the assembly process, so it's fairly bare. But what we have back here at the very end is the radiator. Now this radiator has a capacity of about 150 gallons of coolant.
Impressed? Check out what's under the hood.
Well, what we have here is an example of a very large 16-cylinder diesel engine. Now this one's turbocharged and after-cooled. It produces about 2,300 horsepower, and when it's in operation in our loader, it's going to consume fuel at the rate of about 50 gallons per hour.
The diesel engine turns a generator which actually supplies power to the 4 electric traction motors, providing propulsion. Massive 16-inch hydraulic cylinders lift the big bucket.
We could dig an Olympic-sized swimming pool in just a few scoops. I know we just have to be the envy of all the kids that are playing in their sandbox. We just happen to have the biggest sandbox and the biggest toys to play with.
And how fun would a sandbox be without a dump truck? One of the reasons for designing a bigger loader was the advent of a bigger dump truck. In 1999, the Liebherr Company introduced the T282, becoming the largest dump truck in the world. The massive 282 can haul 400 tons of material. Empty, it weighs 465,000 pounds, and it stands some 24 feet tall. Drivers compare it to driving a 4-bedroom house. Of course, most domiciles don't do 40 miles per hour in the straightaways.
The steering wheel is a little harder to turn, but otherwise it's like driving an automatic transmission car. You put it in forward, mash down on the throttle, and go.
You can add this to your sandbox for a mere $3.5 million. Precision Mechanics takes 6 weeks to assemble the 282.
The frame is the most critical element of the truck that we build. We use a high tensile steel that allows us to lead the industry in the hours of warranty. Our frame is both lightweight and very durable. The frame is 42,000 pound frame, and we're able to carry up to 400 metric tons of load, which is the industry's biggest truck.
Like the L2350, the 282 has a monster engine that can consume 1,500 gallons of fuel a day.
As you can see, this is the front suspension portion of the truck right here. These are the 5-disc caliper brakes that we use, much similar to what you have on an automobile, except our brakes are probably 100 times larger than what you have on your car. Our front suspension weighs about 12,500 pounds, and a normal automobile in and of itself weighs about 2,500 pounds, to give you some idea of the magnitude of what we're talking about.
Liebherr assembles the trucks for road testing. The company believes their trucks run circles around the competition. Whether hauling, lifting, or scooping, these big machines are there to do the grunt work. Next, lots of giant machines that add up to the biggest machine afloat. While many of the world's biggest machines are relegated to incessant toil in some isolated mine, this colossal machine is on a perpetual vacation. Royal Caribbean's Voyager of the Seas is the world's biggest cruise ship. This machine is as tall as a 20-story building. Its job? To shuttle sun-seeking tourists around the Caribbean on week-long excursions.
The Voyager of the Seas at 137,576 gross tons is about 30% larger than any other cruise ship afloat. The Voyager was launched in Finland in 1999. It is a mammoth 3.5 football field length.
Shipbuilders labored for 2 years on the Voyager. Engineers encountered several structural challenges. The hull alone is built of 300,000 pieces of steel. Lounging poolside, you may not believe this floating city is one massive machine. Or more correctly, a number of systems working together as a machine. But consider this. Unseen by pampered passengers are the guts of the machine. A labyrinth of pipes, wires, and ducts that keep the ship breathing.
There is a lot of equipment when you go down in the engine room, because you have the diesel have their own lubricating oil system. Then you have the hot water heating system for the hot water all over the ship. Then you have all the sewer system.
Shipbuilders used 87 miles of pipe, 1,864 miles of electrical wire, and 61,000 electrical outlets to fashion the finished vessel.
Now in this desalination plant, the water which are produced is used all over the ship for drinking, showering, food preparation, everything.
The desalination plant produces 500,000 gallons of fresh water a day by using heat from the engines to boil seawater.
Now this is one of our main diesel engines, one of the 6 engines we have. You can clearly see it's almost as big as a school bus.
The diesel engines drive electric generators which provide power to electric motors that spin 3 propellers or screws, each about 18 feet in diameter. On the underside of the ship, the motor, shaft, and screw are self-contained in a unit called an azipod, which works somewhat like the world's largest outboard motor. The ship has 2 azipods, which can turn 360 degrees, and 1 fixed propeller. Maximum speed at sea trial was a little over 25 knots, which is again a little more than 28 miles per hour. And it doesn't sound very fast, but for a ship this size, it's quite fast. You can easily water ski behind us. Just don't fall, because we probably won't have time to come back and pick you up. If you're on a ship, water is great. But once, monstrous machines were built to evacuate water where it wasn't wanted. The bottom of a mine. In the late 1800s, an iron ore deposit of superb quality was discovered near what is today Iron Mountain, Michigan.
There was a time when the Chapin mine in Iron Mountain was known world over. We were the leading producers of ore in the world for a few years. Immigrants would come to Ellis Island and they'd have a cardboard sign around their necks and it would have Chapin Mine, and they knew where to send them.
The Chapin mine turned out to be one of the most productive and one of the wettest in history. Mine owners found themselves in hot water. The shaft was several hundred feet deep, putting it below the water table. Ground pumps couldn't keep up, and the mine flooded. If the shaft was to go any deeper, they would have to find a far larger pump, and the mine was too valuable to abandon. The tin mines near Cornwall, England, have been using giant pumping engines for many decades. Operators turned to the E.P. Alice Company of Milwaukee to build a gargantuan Cornish pumping machine, fashioned after the ones in England. The company delivered one of the largest and heaviest pieces of equipment of its kind. The massive steam engine has a 40-foot diameter flywheel that weighs 160 tons. Its boilers required 11,000 tons of coal annually. The engine was connected to pumps at various depths, some as deep as 1,500 feet. The engine was designed to run slowly, only 10 revolutions of the flywheel a minute. But with each stroke, gushed 300 gallons of water. That's 3,000 gallons a minute, 4 million gallons a day. The engine displaced so much water, it created a stream running through the middle of town. The pumping engine served for 9 years and was moved once before being replaced by electric pumps in 1914. Designated an historic engineering landmark, the engine still stands at the Cornish Pumping Engine and Mining Museum in Iron Mountain. A tribute to the area's history and a monument to a time when steam ruled supreme. Next, harnessing Mother Nature. Machines designed to ride the wind and unlock the secrets of the universe. Just west of Palm Springs, California, a city famous for spas, golf courses, and retired movie stars, stands one of the most productive farms in the country. But this farm doesn't harvest corn or wheat. It harvests the wind. This is a wind farm, and its machines are some of the biggest in the world. Planted here are thousands of electric wind generators. Some perched on towers nearly 200 feet tall. Think of them as windmills on steroids. The idea is to take the incessant wind that blows through a desert pass here and transform it into usable electricity.
The machines behind us, the diameter of the rotor is large enough where you could put a 747 wingspan in there. The blades are in the range of about 9 tons apiece. Just the hub of the rotor is about 9 tons. So when you add this all up, there's about 60 tons of equipment up in the air on top of that tower. This tower is 180 some feet. Our large generators will generate about 4 million kilowatt hours a year, which is enough to power about 400 households for the year.
People have been looking to harness this free resource for centuries. The Persians were the first to apply wind power to irrigation and milling around the 5th century AD. By the 12th century, windmills spread through Europe. The Dutch relied on windmills to mill grain, pump water, and drain lowlands. But it wasn't until the late 1800s that wind power was applied to electricity generation. Charles Brush, an inventor from Cleveland, Ohio, probably built the first big wind generator. Brush's windmill was massive, with a 50-foot rotor diameter. The 12-kilowatt generator charged batteries in the basement of his mansion. It ran for 20 years without trouble. Still, wind electricity was zapped in the early 20th century by large power plants and an extensive electrical grid. It wasn't until the 1970s energy crisis that wind power started spinning again. Today, Europe and America lead the world in wind electric production.
The rotor you're looking at now is off of a 1 megawatt N54 wind turbine made by Nordex. The diameter of the blades are 50 meters, which is about half a football field. When these blades start turning, they come down this main shaft, which rotates into this 3-ratio gearbox. There's a high speed on this gearbox, which in thus turns a generator, and that's what starts making electricity for this wind turbine.
The Nordex company of Germany builds the largest production wind turbines on the planet. This massive machine isn't even the biggest that Nordex builds. In 2001, the company started producing the world's largest production wind turbines. 2.5 megawatt machines with a rotor diameter nearly the length of a football field. And the company has even bigger plans.
Right now we have in Nordex under development a 5 megawatt turbine that's just monstrous for offshore projects. In the future, everything is going up in size. They're going to be bigger, they're going to be taller, they're going to generate more electricity. It's gotten to be where it's competitive with conventional fuels. And of course, our fuel is free. The wind is free. It just blows forever.
Although wind power is efficient and environmentally friendly, startup costs are significant. And if the wind isn't blowing, electricity isn't being produced. There isn't yet a perfect way of producing electricity. But many scientists believe the greatest potential of inexhaustible energy might one day come from thermonuclear fusion. Fusion powers the sun. Unlike fission, the heavy element reaction that powers nuclear plants, a fusion reaction forces hydrogen isotopes to combine into a heavier helium atom. In the process, a little bit of matter turns into a lot of energy, but without radioactive byproducts. To learn more about the physics of fusion, Lawrence Livermore National Laboratory in Livermore, California, is building the world's most powerful laser. A stadium-sized machine that will create fusion in the lab.
It has 3 purposes. First purpose is to ensure the safety and efficacy of our strategic nuclear stockpile without nuclear testing. The second is to provide, hopefully in the future, a limitless source of pollution-free energy. And the third is to explore physics and science in a regime that we've never been able to before.
The machine, called NIF, after the National Ignition Facility, aims 192 laser beams at a target the size of a BB. The intense heat and pressure forces 2 hydrogen isotopes to combine, creating fusion. The fuel pellet is housed inside a 33-foot diameter target chamber, fitted with diagnostic equipment.
We take electricity off the grid, bring it into the power conditioning system. The power conditioning system is like a giant battery. We discharge this energy into a flash lamp. We have 10,000. Each one of these is around 7 feet high. And what we do with that light is we put it into the laser glass. It absorbs all that light and turns it into laser energy. And that laser energy is then transferred through the system all the way to the target chamber behind me. That target chamber converts this light, which is ultraviolet, into X-ray light and puts it on the target itself.
Voila, fusion. For the nanosecond that the NIF fires, it's discharging 1,000 times the energy that the entire Earth is using during that same billionth of a second. The amount of electricity required to charge this mighty machine before the shot? A mere $5.
This is where the actual laser beam in our facility is born. This is the actual only real laser in what we call the laser system. The beam starts out as a single beam, and that beam is split basically into 192 beam lines. The rest of the building is filled full of laser amplifiers, which takes this small laser pulse and amplifies that pulse over 1 million times, which then is propagated off to the NIF target chamber.
The laboratory has high hopes for the NIF, even before it becomes fully operational in 2008. But the NIF has many opponents. The machine is several years behind schedule and $1 billion over budget. Some critics don't believe it will work once completed.
The issue of will NIF work is always the great question. And the answer is NIF will work. And the amount of attention that will be poured onto this great physics experimental facility will allow us to go places that no one has thought of today.
It's not surprising that the NIF, another one of our biggest machines, is shrouded in controversy. For the last 100 years, controversy has shadowed these giants as we used and sometimes misused them. We've relied on them to build great engineering works and keep the world running. No doubt we will continue using them to move Earth, haul coal, generate electricity, and shuttle the shuttle. And no doubt they'll continue to grow. And perhaps environmental responsibility will continue to become a larger part of our largest machines.